Let's continue in our mole unit. In this section, you will learn how to calculate percent composition, empirical, and molecular formulas. The pie chart that you see in front of you is actually the percent composition by mass of air. Notice that air is a mixture of gases, predominantly nitrogen gas at 78%, followed by oxygen gas at 20%, water vapor at 1%, inert gases, mostly argon, at 0.97%, and carbon dioxide and other gases with the remaining 0.03%. Percent composition is defined as the percent by mass of each element in a compound, or as seen in the last slide, a mixture. The steps to finding percent composition are really easy. The first thing you're going to do is you're going to add up the mass of each element within the compound to get the mass of the compound. This is the molar mass that we have calculated in earlier times. We're then going to divide each element's mass by the mass of that compound and multiply it by 100. At the bottom you can see the formula that we're going to use. Let's do an example together. We're going to calculate the percent composition of each element found in calcium carbonate. In order to do that, you have to have the correct chemical formula of calcium carbonate. And by now, we should be really good at coming up with that formula. Remember that calcium is a positive 2 ion, carbonate is a minus 2 ion. They're going to come together in a 1-to-1 ratio. Knowing that formula, we can now calculate the molar mass. Remember that calcium, if you go to the periodic table, has a mass of 40.01 grams per mole. Carbon, 12.01 grams per mole, and oxygen, 16 grams per mole. We're going to multiply that by 3 because of the subscript. That gives us a grand total of 100.09 grams. Now all we're going to do is take the mass of each element and divide that by the molar mass of the compound and multiply 100. 12% carbon, 40.04% calcium, and 47.96% oxygen are our answers. Notice that if we add all three of these together, you will get 100%. Let's take a look at another problem, but this time I'm not going to give you the chemical formula. Instead, I'm going to tell you that the compound contains 29 grams of silver and 4.30 grams of sulfur only. Using the idea of the law of conservation of mass, if my chemical formula is only going to contain silver and sulfur, they're going to react in a certain way to produce that compound. Since I know silver is 29 grams, and sulfur is 4.30 grams, I know that silver sulfide has to be 33.30 grams in mass. According to the law of conservation of mass, mass is conserved in a chemical reaction. Now that I have the molar mass, all I'm going to do is take the mass of each element and divide it by the molar mass and multiply by 100% to get 87.09% of silver, 12.9% of sulfur, and once again, if I add these together, I'm going to get 100%. Notice that this has only been taken to 3 sig figs, and that's because the minimum number in the numerator was 3 sig figs. I want to take a few moments to talk about a special compound called a hydrate. A hydrate is an ionic compound that has water trapped in its crystal. In the middle of the page, you can see 3 examples. The first one is copper 2 sulfate, pentahydrate. The second one is magnesium sulfate, heptahydrate, and the last one is cobalt 2 chloride dihydrate. Notice how I named these compounds. I took the ionic compound and named it like I normally would, and then I took a look at how many waters were actually attached to that single crystal, and I used the covalent prefix in front of the word hydrate. 5 is penta, and then of course there's the hydrate. If I go back to the last example, this ionic compound is called cobalt 2 chloride. There are 2 waters, that prefix is di, I added the hydrate to represent the water. There are 2 water molecules attached to every 1 cobalt chloride crystal. Now, if I heat the hydrate, all that really happens is the water is removed, and it leaves behind just that ionic compound, which we call the salt, and that has a name called the anhydrate. So if I took the copper sulfate pentahydrate and I applied heat to that reaction, and we can use a triangle above the arrow to represent that, all that would happen is the water would separate from the copper sulfate crystal, and then, of course, it would evaporate away, leaving behind just the anhydrate. We just talked about hydrates because it's very common to actually calculate the percentage of water found in a hydrate. So let's take a look at the example seen on this page, which is copper 2-chloride dihydrate, which has a molar mass of 170.48 grams. So how did that number come about? Well, let's figure out the molar mass. 1 copper is 63.55 grams. We've got 2 chlorine at 35.45 grams. And we also have attached to that 2 waters. Now, water has a molar mass of 18.02 grams. And if we multiply that by 2, that will end up giving us 36.04 grams. I'm going to add that to the 63.55 and the 70.90 from the chlorine. And that's how that 170.48 grams comes about. Now all I have to do is come up with the mass of the water, which we just found out was 36.04 grams, divide that by the total mass of the compound, multiply it by 100, and we find out that there's 21.14% of water in a copper 2-chloride dihydrate crystal. An empirical formula is a chemical formula showing us the simplest whole number ratio of moles of elements, represented as the subscripts. If we take a look at the actual formula for hydrogen peroxide, actual formulas are called molecular formulas, you will see that it has a formula of H2O2. We can simplify that formula into HO. That is considered the empirical formula, the simplest ratio. Sometimes empirical formulas are real actual compounds that exist, and sometimes they're just the simplest ratio that is broken down from a molecular formula. How do we calculate an empirical formula? Well, there's a little rhyme that will help you with the steps, and it goes something like this. Percent to mass, mass to mole, divide by small, multiply till whole. Let's try that one more time. Percent to mass, mass to mole, divide by small, multiply till whole. That rhyme will get you through the 4 steps needed to calculate the empirical formula. The first thing we're going to do is we're going to assume we have 100 grams of the sample of the compound. That means that all we have to do is switch the percent sign to grams. That's the first part of the rhyme, percent to mass. We're then going to convert each element's mass into moles. Second part of the rhyme, mass to mole. Then we're going to divide each element's mole amount by the smallest mole amount in the entire problem. The answers that you get here will be the subscripts of the elements within the compound. That's why the third part of the rhyme is called divide by small. And then the last part of the rhyme, multiply till whole, is actually an optional step. It will only happen if the mole ratios that we just talked about in step number 3 do not fall within 1/10 of a whole number. In that case, we will have to multiply each amount by the smallest whole number that will give us either a whole number itself or a number within 1/10 of a whole number. That last step sounds a little confusing, but it really is not too difficult. So let's do a couple of examples to see how this all plays out. A typical problem is what we see at the top. What is the empirical formula for 40.05% sulfur and 59.95% oxygen? First thing we're going to do is percent to mass. We're going to switch our percent sign to grams, assuming we have that 100-gram sample, and you can see that in this first part. We're then going to convert the mass to moles. In order to do that, you need to divide each element's mass by its molar mass. And we end up getting these answers right here. It's really important at this stage that your answer reflect the correct number of sig figs. And since 4 sig figs is the starting amount of each of the elements, we will go to 4 sig figs in our answer. Now what we're going to do is we're going to divide each of the mole amounts by the smallest mole amount that we see. In this case, between these two, it's going to be 1.250. So you can see in this second part right here, I'm dividing 1.250 by 1.250 to get a subscript of 1, and 3.747 divided by 1.250 is going to give me 2.99. Now, this is within a tenth of a whole number, and so that allows me to round it up to 3. And so my correct chemical formula is SO3, otherwise known as sulfur trioxide. Some of you might have thought that this was the sulfite ion, but there is no charge to this. This is a molecular compound. Let's do another one. What is the empirical formula for 43.64% phosphorus and 56.36% oxygen? Once again, the first thing we're going to do is switch our percent sign to grams. We're then going to divide each element by its molar mass to get its mole amount. Notice that both of these have 4 sig figs, and so my answers go to 4 sig figs. I have to divide by the smallest number, which between these two will be 1.409, and you can see that happening in the second step right here. That means I get a 1 for sulfur. But this time, when I divide 3.522 by 1.409, I get 2.49. And that 4 is not within a tenth of a whole number. It's almost 5/10 away from a whole number. So we cannot round that up to 3 or round down to 2. We are going to have to do that fourth optional step, multiply till whole. So we need to come up with a number that we can multiply by each of these values right here that will get me to a whole number exactly, or at least within a tenth of a whole number. Now we know 2.5 times 2 is about 5, and so that's the best choice for us at this point in time. Remember, you want to find the lowest number that will get that decimal to be whole or within a tenth of a whole. And you have to multiply it by both subscripts. So in this case right here, 1 times 2 gives me 2, and 2.49 gives me 4.998, which is within a tenth of a whole number, so I can round that up to 5. And here I have my chemical formula of diphosphorus pentaoxide. Remember, with molecular compounds, which are covalent compounds, we use prefixes. So molecular formulas are the actual true formulas of the compound, and they are usually multiples of the empirical formula. They could actually be the empirical formula themselves as well. If we take a look at N2O4, I'm going to tell you that that's a molecular formula. It's the actual formula that exists. I can simplify it by factoring out a 2 as these subscripts, and I get NO2. So NO2 is the empirical formula, the simplest formula that exists between nitrogen and oxygen. And N2O4, dinitrogen tetraoxide, is the molecular formula. If we were to look at the chemical formulas more clearly, you will notice that the molecular formula is 2 times bigger than the empirical formula. You'll see that that will also be the case in its mass. So in this chart, we have 3 different compounds, formaldehyde, acetic acid, and glucose, and they have different molecular formulas, actual formulas. Formaldehyde is CH2O, acetic acid is C2H4O2, and glucose is C6H12O6. Notice that they have the same empirical formula, the same simple ratio of atoms, but their molecular formulas are different. Notice in this first example right here that the molecular formula is the same as the empirical formula. So the actual formula is already in its simplest form. If we take a look at acetic acid, we can actually factor out a 2. And when I do that, that leaves me with CH2O. So acetic acid is 2 times larger than that empirical formula of CH2O. For glucose, I can factor out a 6, and that will give me that same ratio. So how do we calculate this molecular formula? It's also very simple, but there are some steps that you need to follow. The first will be to find the empirical formula. Sometimes it's given to you, sometimes you have to calculate it on its own. But once you have the empirical formula, you just need to get its molar mass. That's going to be abbreviated as EFM. You're going to find the mass of the actual formula, which will probably be given to you in the problem in grams. It's called the molecular formula mass, and we're going to give it an abbreviation of MFM. Now, if we divide the MFM, which is the true actual formula mass, by the empirical formula mass, the simplest formula mass, we'll get a factor. And all we have to do is multiply that factor by the empirical formula to get the molecular formula. So what does this look like? Well, let's take a look at a problem. What is the molecular formula of a compound whose empirical formula is CH4N and has a molecular mass of 60.12 grams per mole? So remember we said we needed 2 things. The first is the empirical formula, and what we'll do with that is get the molar mass, which you can see I've done in step 1. The second thing that you need is the molecular formula mass, which most likely will be given to you, which it is in this problem, 60.12 grams. Now we know that that molecular formula is usually a multiple. Sometimes it's the same as the empirical formula, but usually a multiple, so it's always going to go on top. We're going to divide the molecular formula mass by the empirical formula mass. And that gives us a factor of 2, which we then multiply by the empirical formula to get the new molecular formula, C2H8N2. As always, lots of practice in class. Make sure that you're working through those problems. You know how to do these steps. Get help when you need them. And you'll find that these are actually quite fun to do.